All right, let's dive right in. We're going under the hood of the Linux kernel to explore the system that honestly runs the entire internet. It's like a massive digital post office, managing the billions and billions of data packets that make up our digital lives. We're talking about the TCP/IP networking stack. Have you ever really stopped to think about it? You click a link and boom, a web page just appears. You hit send on an email and it just vanishes off to its destination. It feels totally instant, almost like magic, right? But underneath that super simple action is this lightning fast, incredibly complex journey, and the whole thing is orchestrated by the kernel. So, the best way to wrap your head around the Linux networking stack is to picture a giant, hyper-efficient digital post office. Seriously. But instead of paper letters, it's dealing with these tiny digital envelopes we call packets. Its only job is to receive, sort, address, and deliver a constant, nonstop flood of these packets with maximum speed and, minimum fuss. Okay, so to really see how this digital post office works, let's follow a single piece of data. We'll trace its journey from the moment it leaves an application on your machine and heads out into the big, wide world of the internet. It all kicks off when an application, say your web browser, needs to send some data. It makes what's called a system call, which is basically a special request to the operating system, handing over its message. The kernel's socket layer immediately grabs that data and wraps it in a standard container, a SKBuf. This is our digital envelope. Next up, the TCP layer acts like the mail sorting room. It chops big messages into smaller, numbered pieces so they can be put back together reliably on the other end. Then, the IP layer comes in and stamps the final destination IP address right on the envelope. Finally, the packet gets handed off to the link layer, which gives it to the network card driver to be zapped out as electrical signal. Now, this quote here, it might seem a little dry, but it actually reveals a core philosophy of the kernel: speed through delegation. The entire system is built to pass off work whenever it can. In this case, it's talking about checksum offloading. So instead of bogging down the main CPU with all the math needed to check if a packet is corrupted, the kernel just assumes the network card has special hardware for that. It just hands off the task. This saves so many precious CPU cycles for the stuff you actually care about, like your applications. But look, sending packets out efficiently is really only half the battle. Modern networks are an absolute fire hose of incoming data. Handling that constant deluge without grinding the entire system to a halt, well, that's one of the kernel's biggest challenges. So how does it solve this incredible need for speed? Oh man, the old way of handling incoming data was a performance nightmare. Imagine the postmaster's phone ringing for every single letter that arrived at the post office. That's what we call an interrupt storm. And at high speeds, it would just completely crush the CPU. The modern solution is something called NAPI. With NAPI, the network card basically just raises a little flag that says, hey, a whole bag of mail just got here. The kernel sees that one flag and then comes over to process the entire batch all at once. It avoids thousands of tiny individual interruptions. It's so much smarter. Now, the really crucial thing to get here is that NAPI is a hybrid approach. It uses a single hardware interrupt to get its attention, to kick things off, but then it immediately switches to software polling, which is just actively checking for more packets. This lets it clear out the hardware's memory buffers in one super efficient burst. It really gives the kernel the best of both worlds. You get the immediate, hey, look at me, of an interrupt, but with the high throughput power of polling. And this just goes to show you that NAPI isn't working alone. The kernel has this whole performance toolkit, a whole bag of tricks. You've got TCP segmentation offload, which lets the hardware do the chopping for outgoing data. We already talked about checksum offloading. Then there's receive side scaling, or RSS. This is a hardware feature that's basically like opening up more service windows at the post office, spreading the incoming packets across multiple CPU cores. And for hardware that doesn't support that, there's receive packet steering, which is a clever software version that does the exact same thing. So we know the tools the kernel has to keep up with these insane speeds. Now let's flip the script and follow the return journey of an incoming packet from the wire all the way back up to the waiting application. This journey starts the second the network interface card, the NIC, receives the packet. It uses something called direct memory access, or DMA, which is an awesome feature that lets it place the packet data directly into RAM without bothering the CPU at all. This is what triggers the whole NAPI mechanism, and the driver's poll function gets scheduled to run. It swoops in, scoops up a whole batch of packets from memory, and starts decapsulation, which is just stripping away the link, IP, and TCP headers, layer by layer. It's literally like opening the envelope until only the original data is left. Finally, the kernel looks at the port number from the TCP header to find the exact application that's waiting for this data and delivers it.
But on a modern multi-core system, there's actually another layer of optimization. It's not just about getting the packet processed fast. It's about getting it processed in the right place.
And this is where receive flow steering, or RFS, comes into play. The logic here is so simple, but it's incredibly powerful. If your browser is running on, say, CPU Core 2, RFS does its absolute best to make sure that network packets destined for your browser are also processed on CPU Core 2. And this is all about something called cache efficiency. Moving data between the caches of different CPU cores is actually a pretty slow operation. By keeping the application and its data on the same core, RFS avoids these slow cross-core transfers, and that provides a subtle but really significant performance boost.
So when you put all of these pieces together, the layered stack, the hardware offloads, NSAP, the smart flow steering, what you get is this incredible, invisible engine that powers the modern internet. But what does this whole operation actually look like from the kernel's point of view?
This is it. You're looking at a little snippet from a special file, /proc/net/TCP. This is the kernel's own personal ledger of every single active TCP connection on the entire system. You can see the local and remote IP addresses and ports, and most importantly, the connection state. Here, it's O1, which just means established. This isn't an estimate or a log. This is the live, ground truth state of the kernel's digital post office at this exact nanosecond.
The Linux network stack is, without a doubt, a marvel of software engineering. It's scaled from kilobits all the way to gigabits per second. But technology never stands still, does it? As network speeds start pushing towards terabits per second, that's 1,000 gigabits, it leaves us with one final huge question. Which part of this incredibly optimized system is going to be the next bottleneck that the world's kernel engineers have to figure out how to solve?